experiment number 5, which is this week's schedule. And it's timely because we are concentrating on acid-base chemistry in lecture. So we've been talking about acid-base chemistry for the past couple of weeks. And so your last experiment for this particular section is to determine the unknown, to determine the identity of an unknown weak acid through titration. So let me go ahead and give you the background information for this particular experiment. Look at the grading rubric. So you have a guideline of how I'm going to grade it. And if you follow that, you pretty much get the majority of the points. It'll just depend on the content that you put down in your report. Okay, take a look at the feedback I gave you on your last few experiments, because that's important. And remember that you can't just paste a document using the text editor in Canvas. You actually need to copy it if you put in a word processor and then paste it in, because we are using a plagiarism detection, and that's true for all of Chem 201. And if you just paste it in as a PDF file, that's not going to work, and I'm not accepting it that way. Okay, so please keep that in mind, that if you put in a word processor, then it's in there as a text. What you need to do is just copy that and then paste it using the editor. And the editor is pretty straightforward. What you will get in the editor are tools like this, where you can paste things, copy and paste, and then you can write documents. You can put images in there. You can put YouTube and everything. You actually have a text, an equation editor here. So you can put an equation in there. You can create tables, and when you create tables, make sure you have a grid there. Make sure that when you add a table like that these lines are not invisible, okay? Because then when you actually publish it, Canvas is not very good in making the format. And so if you write something in, you could also center it, okay? Or justify it on the right or the left. So it's important that you make full use of the editor in Canvas, because that's what you guys are graded on. So please make sure you do that. And if you put it in a Word document or a Google document, then you can just copy and paste it and then make minor revision depending on the editor that is in, so that Canvas has. So let me go ahead and close this. Remember that we use the UniCheck plagiarism detector, and it looks at everything that this institution has in terms of the files that have been submitted. Okay, so please take a look at that. So this is the background information for experiment number 5. Experiment number 5, if you were doing it in lab, it would probably take 2 days. That's because there are 2 methods that you will use to identify your unknown. This right here, if you click on that, takes you to Logger Pro or Vernier, and they just give you a video of what a titration experiment would look like. You can preview that and kind of see what's going on. Okay. You can also look at the PowerPoint, which I will be sharing with you shortly. And then this is just the write-up or the experiment number 5 in terms of the background information, in terms of the pre-lab questions. Okay, some of you keep skipping the pre-lab questions. Look for the pre-lab questions. It's generally somewhere in the body of the experiment. Sometimes it's after the background information, sometimes it's after the procedure section, but there's generally a pre-lab. Then it describes the two methods that you guys will be using in this experiment. The first method is just a straight titration. What you do is you have a pH probe and you generate a titration curve for while you are titrating your weak acid. And then there's a second method where you titrate it to the equivalence point using a acid-base indicator, okay? And the acid-base indicator will change colors and you know when to stop the titration. And there's going to be a technique that you guys will follow in order to figure out what the pKa is for your unknown acid. So this is method 1, and then later on here you have method 2 right here. And based on the two methods, they should somewhat agree with each other, okay? And then you consolidate those data to determine the identity of your unknown. So that's the background information. Let me give you some information on this particular experiment. The determination of the Ka. Why do we need a Ka? Because Ka are generally unique for that acid. That acid has a hydrogen, maybe 2, maybe 3, okay? It depends on the chemical that you have. And it's going to be fixed. It's like a property. It's like the density or the boiling point or melting point of a substance, okay? It's a physical property associated with that particular chemical. So the Ka is unique for that chemical. And of course, its molar mass is unique for that chemical because it contains a certain amount of atoms that are bonded together. Using the Ka and the molar mass, you are given a list of acid. You're going to match the Ka and the molar mass to a particular list, and you guys are going to be able to identify the identity of that acid. That's basically your lab, okay? So the job of this experiment is to first determine the Ka and then figure out what the equivalent volume of the titration is. Why do you need the equivalent volume? Because if you know the equivalent volume, then you know the moles of the titrant you're adding. If you know the moles of the titrant you're adding, then you know the moles of the acid. If you have the moles of the acid, then all you really need is the mass of the acid, because grams per moles, you guys know, is the molar mass. So how do you get the mass of the acid? Well, you weigh it at the beginning of the experiment. You have an acid, it's a solid. It's a acid that's a salt. Okay, we talked about salt in lecture. You take that salt, or you have an organic acid that is a solid, and that will have a certain molar mass. And the molar mass can be determined by titration. Okay, so let's take a look at this. This is just the background information. The objective of this particular experiment is to analyze an unknown acid via titrimetry, okay, via titration, in determining both the Ka and the molar mass. So remember that an acid is a chemical that wants to release a hydrogen. So you can force that hydrogen to be released and then measure the strength by which it holds that hydrogen. And if you do the experiment properly, you can figure out that strength, which we call the Ka. So this is an example right here of the change my pen. This right here is a typical reaction of an acid in water. An acid in water will dissociate. Why? Because it's an electrolyte. Electrolyte by its nature are going to dissociate. If you don't have an electrolyte, if you have, say, a non-electrolyte, then it's not going to dissociate. It's not going to form ions, a non-electrolyte. But if you have an electrolyte, depending on whether it's strong or weak, the degree of dissociation will be more efficient if it's strong, less efficient if it's weak. So an acid in water will dissociate whether it's strong or weak. That's just the nature of an acid. And you can write the mass action expression. And that mass action expression is called the Ka. the equilibrium constant for an acid. Okay. The other thing that you should know is that there is a condition when you have both the acid and its conjugate pair present in the solution where you can use, which you have a common ion effect, okay? And then you can use something called the Henderson-Hasselbalch equation. But nevertheless, what you can do is you can measure the Ka via the mass action expression, or you can measure the Ka using the condition in which both the acid and its conjugate are equal. So you generate a titration curve. You find the equivalent volume, and then halfway to the equivalent volume, you can reach the pH, and that pH equals the pKa of that acid. That's method one, okay? You guys are gonna generate you're going to watch the video of the titration curve that's being generated. You're going to look at the titration curve, and from that data, you're going to find the pH at halfway to the equivalence point, and that pH equals the pKa. So the pKa can give you the Ka value, and then you can compare the Ka value to the literature and then pinpoint your acid that you have. So this is the math that goes on when you are 50-50 or when you're halfway to the equivalence point. What goes on is that you're adding enough titrant so that you're only neutralizing half the acid. And when you neutralize half the acid, half of it remains and half of it converts over to its conjugate. When that happens, of course, then we have this, where Cb stands for conjugate base and Ca stands for conjugate acid. Remember, conjugate pairs only differ by one hydrogen. When they are equal, that term goes to 0, and now you have pH equals pKa. So that's important. That's the criteria by which you guys are determining the pKa or the Ka of the acid in method 1. Okay, so this is what the titration curve feature will look like. You're going to start low, you're going to go through a buffer, you're going to hit the equivalence point, and then you're going to tail off. So the experiment itself will require monitoring the pH and then titrating way past the equivalence point, so you can see this tail. In the past, what students would do, they would stop right here, and that's not good because you don't know whether or not it's still doing this or something. You need to see this tail right here, so that you can define the inflection point. You can see where the slope of the curve goes from positive to negative, or you can take a first and second derivative. But the video itself will go past the equivalence point, and then you guys can analyze this. Then there's another thing that is important here. Okay, there's another thing that's important here. And the other thing that is important is the following. Suppose we have our titration, and it looks like this, and we know the equivalent volume of the titrant. Okay, now remember the pH at the equivalent volume does not equal the pKa. I need to say that over and over again, because as much time as I say it, some of you are going to say that, oh yeah, my pKa is equal to this, and then you're going to be comparing the wrong pKa. It's halfway. This is halfway to the equivalent volume. It's halfway to the equivalent volume, and so at that point, extrapolate here, that's where the pH equals to pKa. But that's only one of the data that you need in order to determine the identity. The other is the molar mass. So this is what you need right here, the equivalent volume. Why do you need the equivalent volume? Because your titrant is sodium hydroxide. Okay. And you're going to know the concentration of that. Let's say it's 0.200 molar, just for the sake of discussion. If you know the volume at the equivalent point, then you know the moles at the equivalence point. The molarity remembers moles per liter. You multiply that by a volume, you get moles or millimoles. Whether you're using moles or millimoles, the thing is that moles of your base is equal to the moles of your acid. And yes, this acid is weak, but they are still equal, because the strong base, sodium hydroxide, will demand all the hydrogens from that weak acid. So there's like 32 weak acid. It'll demand all the hydrogens from that 32 weak acid. It'll demand all the acid. So at the equivalence point, the moles of the acid and the moles of the base are equal. If you have the mass of the acid, and how do you know that? Because you weigh the acid at the beginning of the experiment and you divide by the moles of the acid. Then you have the molecular weight of the acid. So if you have the molecular weight and the Ka, you can use the list that's provided to nail down the identity of your unknown. It's a simple experiment. The experiment is tedious because you do have to do titration, and you always do a minimum of 3 trials in any experimental procedure. The reason why you do a minimum of 3 trials is, well, there's a couple of reasons. One is that you can reproduce your work. And so if the first one's high and the second one is in the near ballpark of the true answer, then the third one sort of establishes that. Okay, the third one's going to be skewed more often than not to the correct value. So if you do 1 or 2 trial and they're really apart, you don't know which one to believe. If you do a third one, then it'll kind of skew you in one direction or the other. The other thing is that you can do statistics with 3 trials. Okay, you can do statistics with 3 trials. 1 trial just gives you a number. 2 trials, you can do an average. But again, the average really doesn't mean anything. It's just the medium between the 2 values. But a third one, you can do an average, and then you can compare how far each of those values are from the average. That's called a standard deviation. How far does each reading deviate from the average? The greater the standard deviation, the less precise you are. Not very good in terms of the data. But if your standard deviation is small, it means that each of the measurement is very close to the average, which generally means that you have good precision. So we do a minimum of 3 trials, and in this particular lab, that's not an exception. We do 3 trials, and then you can do an average, and then you can take a standard deviation. That's what we try to instill in terms of your lab technique, to not only look at the data, but look at the precision and the reproducibility of that data. Anyway, this right here is how you nail down your unknown, through the Ka and the molecular weight. Okay, so the first technique is you guys are going to do a titration, and the titration will require you to prepare. Well, prior to the video, you would actually prepare a standard solution called KHP. KHP is potassium hydrogen phthalate. And the reason why you prepare a solution of potassium hydrogen phthalate is because this is a very stable chemical. Okay, you weigh 30 grams of it. It's not going to pick up water. It'll be the number of moles in 30 grams, pretty much true. What you can do next is take that KHP, which is a weak acid, and then take your sodium hydroxide and then titrate it to the equivalence point. You will know the mass and therefore the moles of your KHP, potassium hydrogen phthalate. And so when you titrate sodium hydroxide and you reach the equivalence point, you will know the volume at the equivalence point, and then you can back calculate. If you know the moles of your KHP, and that's true, then the volume, the moles of KHP and the volume of the base that you add will give you the concentration of the sodium hydroxide. Why do we need the concentration of the sodium hydroxide? Didn't the lab tech prepare that? And therefore, didn't the lab tech, aren't we going to trust the lab tech's data? No, the lab tech did prepare it, but we don't trust the lab tech's data in terms of the concentration. Why? Because even though he may have prepared it precisely, sodium hydroxide is a base. And for those of you in my lecture, you know that there's carbon dioxide in the atmosphere. Carbon dioxide will get absorbed in the water. The water and the carbon dioxide will form carbonic acid. The carbonic acid will react with the sodium hydroxide in the bottle, especially if it's open, and then it'll lower that concentration. So in other words, he may have precisely determined the concentration of sodium hydroxide for you, but if it's being stored and it's not closed and pumped with nitrogen, the concentration of that sodium hydroxide will drift. And if you're doing precise work, you're going to need the exact concentration. So what do we do to get that exact concentration? We standardize the solution with KHP. Now, you guys don't have to do that because we've bypassed that, but that I just want to mention that that is part of the procedure. If you were doing this experiment at Miramar, you would measure a whole bunch of KHP, a certain amount. You would take the sodium hydroxide, you would put it in a plastic water bottle or a plastic container. Why? Because sodium hydroxide will eat through glass and etch it. You don't want to do that. So you put it in a properly container, a plastic container, and then you close it. And if you're storing it overnight, you pump nitrogen in it so that the carbon dioxide doesn't react with it. Then you take that sodium hydroxide and you start titrating KHP, potassium hydrogen phthalate. The chemical itself looks like this. It's a benzene ring, and it's got 2 carboxylic acid. It looks like this, actually. Okay. So let me do this. This is potassium hydrogen phthalate, this chemical right here. Notice it's got a carboxylic acid, 2 carboxylic acid at the tail. But what we're going to do is we're going to make this particular acid a salt. We're going to make it a salt. And how do we make that a salt? We remove this hydrogen and replace it with potassium. That's why it's called potassium. So the potassium here, this is a negative. Potassium hydrogen phthalate. This right here is the phthalate portion. Okay. So the Ka of this salt, and this is true for your unknown, is not Ka1 because it's not the first hydrogen that we are titrating. It's Ka2 because it's the second hydrogen that comes off. So when you look up your unknowns, a lot of your unknowns will be ionic substance. Make sure you understand which Kas to compare, because depending on whether we give it to you as an acid or the salt, you have to look up whether it's Ka1 or Ka2 that you're comparing your results with. Okay, and I'll talk more about that. Anyway, you guys don't have to worry about that, but I want you to be aware because you might have a question in the future about standardization. You guys are going to trust the concentration of the sodium hydroxide because I made sure that the concentration was correct in the data set. and then you can just look at the data when you watch the video. Anyway, what will happen is that you guys are going to do the titration. In this particular case, you guys are going to titrate it to the equivalence point, or at least know the volume at the you will know the equivalent volume. And at the equivalent volume, then you can say that the moles of the base equals the moles of the acid, which is what I talked to you guys about, okay? And if you know the moles of the base, you know the moles of the acid, and if you take the mass of the acid and divide it by the moles, you have the molar mass. Second piece of data. So this background information here just shows you how that calculation is done. Now, don't follow this list. This is a more extensive list. There's a list in your lab manual. This experiment has been revised numerous times, but I just want to show you what I mean by the Kas of your experiment. If you take a look at this chemical right here, cis-crotonic acid, that's an organic acid. All you have to do is look up the Ka values of crotonic acid. Let me show you where that is. Let me switch. That'll be in your lab manual. Okay, that'll be in your lab manual. Go to my website and find it. So if you take a look at this, it's the same data that you guys are going to find in your lab manual. And you look up crotonic acid right here, crotonic acid, cis and trans. Then the Ka is 3.85 times 10 to the minus 5, or 2.04 times 10 to the minus 5, depending on whether you have one version of that acid or the other. Okay, that's the Ka. But let's take a look at another chemical. Suppose you are given this particular salt, sodium hydrogen oxalate, NaHC2O4. Okay, suppose you're given that salt, or you're trying to find the Ka for that. And then you go to this table that I just mentioned, and you're looking for a chemical with NaHC2O4. And if you look through here, there is no acid with Na. There is none. Why? Because that's the salt. That's the ionic substance. What you will find is H2C2O4. That's oxalic acid right here. Okay. This right here is C2, O4, 1, 2, 3, 4, H and Na. Remember that the formula that I gave you here was this: NaHC2O4. You're not going to find it in this list. What you need to do is you need to remove that and replace that with a hydrogen, H2C2O4, which is just this chemical right here. This chemical right here. 2 hydrogens, 4 oxygens, and 2 carbons. Okay? With the sodium there in NaHC2O4, that's the first hydrogen that comes off. So therefore, you're looking at not Ka1, but Ka2 for that particular chemical. Okay? So if you have a salt, look at the formula. To find the original acid, replace that metal with a hydrogen. Okay, so you can find it within this list, but then replace that hydrogen again with the metal and look at which hydrogen is the one that's being removed. And that's the Ka that you guys are going to use when you make the comparison. That's the key. Okay, so if you have something like sodium bicarbonate, NaHCO3, you're not going to find sodium bicarbonate in this list, but what you will find is carbonic acid right here. Okay, you will find carbonic acid right here. Okay, carbonic acid is right here. And because it's the second hydrogen that's going to be coming off, you're not going to be using Ka1, you're going to be using Ka2. And that's what you are using to identify your unknown. So I hope that's clear, because I know in the past, a lot of students would come up and say, okay, this is the list of the unknowns, but I can't find the Kas for these chemicals anywhere. Well, that's because we give it to you as a salt. It's up to you to recognize which acid that comes from and then figure out which Ka to compare. Okay, so that's important. So let me go ahead and continue on with this. So these are possible unknown acids. Notice that this is a salt, this is a salt. All of this in the list are salts, whereas all of these are organic acids. Organic acids are not salt. They could exist as a solid, and so you can weigh them directly. But most acids are liquid. So how do you make a liquid a solid at room temperature? You convert them to the salt. And then as a salt, they're ionic, and so they'll have high melting point, and they'll be a solid at room temperature. Then you can manipulate them. Okay, so this is the equipment that you guys will be using. Of course, you guys are going to be doing a pH probe, burette, the Erlenmeyer flask, your stock solution, etc. This is what it looks like if you guys were going to be doing the experiment. You got your burette. You got to make sure that both the pH probe and the stopcock of your burette will fit in, because this is where your acid's going to lie. And then you usually have a magnetic steering bar in there, so the solution is homogeneous when you do the titration. So this is method one. You weigh your unknown acid, okay? And you guys will be assigned different unknowns depending on your CSID. You weigh that, then you put it in a container, an Erlenmeyer flask, a wide mouth Erlenmeyer flask, and then you add water. Whether you add 10 mils of water or 20 mils of water, the moles of the acid is already fixed depending on the mass that you have. So adding water does not change the mole. Yeah, it changes the concentration, but you're not worried about the concentration, because at the equivalence point, the moles of the base equals the moles of the acid. You're only worried about the moles. Okay, so adding water here, whether you use 20 mils or 28 mils, it doesn't really matter. Your moles is fixed based on the mass. Then this is method two. In method two, you're going to have a 4 times the amount that you weighed in method one, and then you're going to put it in a volumetric flask, and then you're going to add water. So whereas in method one, you weigh your acid, you do 3 separate experiments with 3 different mass. In method two, you have 1 mass and you put it in a volumetric flask, and then you take aliquots, you take portions and you titrate that. So if you make an error in the mass in method two, your whole experiment is off, okay? If you make an error in one of the mass in method one, then only that particular trial will be affected. So there's pros and cons with these different methods, okay? This is much easier to do. This is more tedious, but it's more reliable in terms of reproducibility or confirming any errors that occurs. Okay, so this is method one again. You're going to have your solutions that you prepared, and there are 3 of them. And then you guys are going to titrate using a pH probe connected to a vernier. And you're going to watch the pH change as you add titrant. And it's going to generate a titration curve like that. The titration curve will tell you the equivalent volume, and you should be able to read the pH equals the pKa at halfway to the equivalent volume. At the equivalent volume as well, and the concentration of your base, you can get the moles of your base, which is equal to the moles of your acid, and then get the molecular weight that way. So that's method one. In the titration curve, you look at the equivalent volume to get the molar mass. You look at halfway to the equivalent volume to get the pKa. You guys are not required to do a first and second derivative on this, because if it was your data, then yeah, you could do it, but you're not required, because you can trust the results to determine your unknown. Okay, but if you were doing this experiment on your own, I would advise you to do a first and second derivative. Anyway, that's method one. Method two is much easier. Okay, method two, you have a stock solution, and then you withdraw from that stock solution an aliquot. You take only, say, 20 milliliters, and you put it in a Erlenmeyer flask, and then you titrate that. But you don't titrate it. You don't titrate it with past the equivalence point. You stop at the equivalence point. You stop at the equivalence point. That's when the solution turns color. Okay, so you stop. Now, you're going to pick phenolphthalein indicator. And phenolphthalein indicator is a good indicator because the equivalence point is going to be above 7, between 8 and about 10, and that's where phenolphthalein changes color. You don't want to use an indicator like methyl red, because methyl red changes between 4 and about 5 pH. And so you would be prematurely calling the equivalent volume before you reach the equivalent point. So we're using phenolphthalein indicator, turns pink. We stop once it turns pink, okay? And then what happens at the equivalence point, and this is the important part, is that all the acid that you had originally, right here, all the acid that you had originally at the equivalent point has now converted over to its conjugate. So this pink solution right here, all you have in there is the conjugate. Yeah, it's going to react with water and everything, but the important thing is that all that original acid has been converted to its conjugate. So if you take an additional 20 milliliters from this acid, an additional 20 milliliters, which is how much you started with when you did the titration, and then put it back into here, then you're forcing these two chemicals, because now, see, when you do the titration to the equivalent, all the original acid is the conjugate. But now what you're doing is you're taking 20 mils of the acid and putting it directly back into that same Erlenmeyer flask. And so what you're forcing is that these two right here are equal. These two right there are equal. And when you have equal amounts of acid and its conjugate, or base and its conjugate, well, guess what? The pH equals the pKa plus the log of the conjugate base over the conjugate acid. This is going to go to 0. So at that point, when you add 20 mils to that Erlenmeyer flask that was at equivalence point that turned pink, it's going to turn clear on you, okay? Because now it's not at the equivalence point anymore, but you got 50% acid and 50% conjugate. You measure the pH at that point, that's the pKa of the solution, okay? So you see, this technique is much easier than the first method, but there's more chances of error as well. So let me repeat method 2. You take your stock solution, because you prepare that. You take an aliquot, let's say 20 mils. You put that in an Erlenmeyer flask, and then you put indicator, and then you titrate that to the first sign of pink. Now you're at the equivalent point. You know the equivalent volume. Okay, You take that Erlenmeyer flask out from underneath your burette, and you add an equal amount of the original acid back to that solution. Now you force the acid and its conjugate to be equal in that solution. You take a pH meter, you stick it in there and you read the pH. That pH is the pKa. The volume at the equivalence point, you can use that volume to calculate the moles of the base, to calculate the molecular weight of the acid. So the equivalent volume is still preserved, okay, because you stop at the equivalence point. You want to record that data. But now you take that Erlenmeyer flask and you force the acid and its conjugate to be equal. And when you measure the pH, that pH should equal the pKa. That's method 2. Much easier than method 1, but again, more chances of error. More chances of error. So let me go ahead and clear this. This is the equivalence point. This is the addition of the acid, original acid, back to that solution at the equivalence point, and then you measure the pH, and that pH is the pKa. Okay, so that's basically the 2 methods, and you're going to use both methods to identify your unknown. Okay, so this is the data analysis. It gives you a summary. And so let me go ahead and show you the video. Yeah, this is it. This is the data and observation section. Okay, the data and observation section. So these are the, this is just a background. This is just the PowerPoint that I shared with you. And then right here is the data set. So I'm going to stop. I'm going to begin right here because this is the procedure for step 1. Okay, you can see that that's what's going on. And then I'm going to stop right here. These are possible unknowns. And I give you lactic acid. The molecular weight of lactic acid is 90.08. And when I look up the pKa, it's 3.86. To get the Ka, remember, you just take the negative of this and raise it to the 10th power. That'll get you that. And then if you move on, this right here is the data for lactic acid. So this is what the data will look like so that you can see how the calculation is done. You can see that, okay? And then this right here is the data for the different unknown. This is unknown number 10. This is unknown number 20 and 30 and 40 and 50. Okay, why are there 5 unknowns? Because one of these is going to be assigned to you. Okay, so this is just the PowerPoint that you should review for this. Let's go back. Let's take a look at this right here. Titration of an unknown with sodium hydroxide using pH probe. This is method 1. Let's get out of that. Okay, method 1, direct method titration. So you can just, you want to make note of the concentrations because I'm not going to, I may give you the concentration, but it's on here in the movie. You got 0.097 sodium hydroxide. That's your base. These are your unknown acids. Okay, these are your unknown acids. Take a look at the texture. They're all white. This is the mass that you guys are weighing. Method 1, direct titration, weigh about 0.1722 grams of unknown acid. Place in beaker, add enough water to dissolve the unknown. Add phenolphthalein, optional. You don't need to do that because you're doing a pH, and then titrate it to the equivalence point. Okay. But before you do the titration, you got to calibrate your pH probe at 4, 10, and 7. And so I think this is the calibration procedure. Make sure you take a note of that because if it's not properly calibrated, your pH will be off. So this is the calibration procedure. See, I'm calibrating at pH 4. You guys did activity number 4B, in which we did the same thing. So take a look at that. Anyway, after the calibration, okay, we test with pH 7, and you can see that it's between, it's at 7 plus or minus 0.1. So that's reasonable. Now we do the titration. And I'm fast forwarding this so that you don't have to wait forever. So you can see how the pH change. And then you want to read the video because it tells you exactly the data that you have. At the equivalence point, it was 19.45 for this trial. And you can see it did turn pink. And now I'm going after the tail end in this particular experiment. And this is the pH when I'm collecting the data here. Anyway, let me go ahead and scrub through. So that was the logger pro. Then I do a second trial and a third trial. And then the data set looks like this. Let me stop here and explain. So for lactic acid, which is what you saw, okay, I didn't do all the acids. I just did lactic acid. So you will see how this experiment is performed. We have trial 1, trial 2, trial 3. These are the mass. The average mass is that. The pKa at the equivalent point, 10.35, 10.51, 10.72. Now you're not going to use the pKa at the equivalent point, but you record it anyway just to see how consistent you are. And then over here, okay, pKa at halfway to the equivalence point. That's the important point. Okay, if you take a look, it's 3.68, 3.88, 3.87. So 2 of these are very close. One of them is sort of far, and that was because it was the first trial. The first trial is always quick and dirty. Second and third, hopefully, are more consistent. And these are the average. So if we know what the equivalent volume is, and we know the concentration of the base, okay, we know the concentration of the base, it's 0.097 right here. The concentration and the volume will give us the moles of the base, which is equal to the moles of the acid. And now if we have the mass of the acid, which is down here, and we divide it by the moles of the acid, we get the molar mass, which calculated as 91.27. You guys should write this all out in the post lab so you can see, but double check your calculations with lactic acid so you know that you're doing the calculations correctly. So that's method 1, and there are 3 trials. Trial 1, trial 2, trial 3, and then there's an average. And then this is method 2, where we have the mass, and the mass will be the same throughout because you're just measuring one mass and you're putting it in a volumetric flask. And then it'll tell you how much volume we are using. Actually, we are using 25 mils, not 20. So the dilution factor is 1/10 of that original stock solution, because the stock solution, that original volumetric flask, was 250. And I'm using 25 mils of that. So it's 1/10 of that, okay? So you have to factor that in your calculation, because you have a mass here of 0.7899, okay? And you're only using 1/10 of it. So you're only using 0.07899 to calculate the mole when you get the molar mass. Anyway, this is the pH at the equivalent point, and this is the pH when you add the acid back to the original. And so it's 3.67 for the first trial, 3.92, 3.87 for that, and the average is 3.82. This pH at halfway to the equivalence should be very close to method 1 to show consistency, okay? And then, of course, let's move on with this video, okay? That's just the data. So let me go ahead and end that. Okay, here it is. So see how I have these acids again, and I'm putting it in a 250 volumetric flask. And here again is the procedure. Weigh it out, put everything in, and then take a 25 mil aliquot, 25 mil aliquot. So you're only taking 1/10 of that original solution. And notice I got both a pH probe and an indicator here, but what I'm going to do is I'm going to stop at the equivalence point. So I went ahead and titrated this, and I stop right here. See how it turns pink? First sign of pink, permanent pink, I stop. pH at the endpoint is 6.02. That's not what I'm using, but the equivalent volume is what I need. Okay, notice it's much less than method 1. Why? Because we're only titrating 1/10 of that mass that we weighed out. We're only taking 25 mils of that 250 mils. So of course it's going to require less volume. Anyway, that's the data that you guys would use. And then here is, again, the procedure. Once we have this, take a look at this, because now that I have it at the endpoint, I'm taking a 25 mil volumetric pipette. I'm measuring it out, and then I'm adding it to this solution that is now at the equivalence point. Okay, so once I have that, watch the pH change. It drops. It drops. Okay, I'm adding 25 mils, and that pH value now is the pKa of this acid because they're equal. Notice I have my magnetic stir in the bottom. So whatever the pH reading is at this point, that's my pKa for this acid. And since this is lactic acid, it should be very close to method 1. In this particular case, it comes out to 3.67. Okay, so that's the procedure that you would use for method 2. You titrate it to the endpoint, and you add an equivalent volume back to that solution, and you read the pH. So that's the movie. Let me get out of that. This is the data right here. This is the data. Before we look at the data, let me go back. Before we look at the data, read this. Your CSID will determine your unknown. If your CSID ends at the last digit is 1 or 6, you're assigned unknown number 10. If your CSID ends, the last digit is 2 or 7, your unknown's number 2. 3 or 8, your unknown's 30. 4 or 9, your unknown's 40. 5 or 0, your unknown is 50. So this might be a CSID. Look at the rightmost digit, and that rightmost digit determines what unknown you guys are assigned to. Okay, so let's take a look at the data. Okay, these are possible acids. Again, this is the data for lactic acid. Again, and these are some Excel equations that you guys can use if you want. This is the data for unknown number 10. We weighed 0.2063 for first trial, 2293 for the second trial, 2103 for the third trial. The equivalent volume was 19.41, 20.06, 19.68. The pH at the equivalent point was 9.33, 9.51, 10.05. And then the pH at halfway to the equivalent is 3.05, 3.22, 3.16. So that's the data that you guys are given. For method 2, and this is true for all your unknown, we weighed 1.0122. Notice that this mass is 5 times greater than method 1. Why? Because we dissolve it in 250 mils. So all the mass will be the same. And then you're taking a 25 mil aliquot and titrating it. And the equivalent volume was 9.15, 9.39, 9.35. The equivalent volume when the indicator turned pink. When you add an acid back to that solution for trial for unknown number 10, it came out to 3.33, 3.02, and 2.97. And what is the dilution factor? The dilution factor is 10. Why? Because we're only taking 25 mils out of 250. So this original solution that is in the volumetric flask, you got to multiply your moles by 10 if you're going to use this mass right here to get the molecular weight, or take this mass and divide by 10 and then use this volume. But there's a factor of 10 in there that you have to know how to use when you do your calculation. Either increase it by 10 or decrease it by 10, but change your volume accordingly. Then you can calculate the molar mass. So that's unknown number 10, unknown number 20, you have the same thing. Unknown number 30, you have the same thing. 40 and 50. And once you figure out your molar mass and your Ka, then you can go to this list right here and then nail down your unknown. That's your experiment, okay? It's an analysis experiment. It's pretty straightforward, but it's calculations that you guys need to do in order to nail down your unknown. Okay, so let's do next. That's your data and observations. This is a summary of what you guys need to calculate. And then your post-lab questions is here. When you have your unknown, you need to go in here, and there's going to be another question in Canvas to nail down your unknown. So let me show you where that is, because you need to announce what your unknown is right here. Submit the identity of your unknown and molar mass. So once you figure it out, click on this and then turn in the identity of your unknown in this page. Okay, you need to do that, and then you're done. Yeah, this is last year, so that needs to be cleaned up, but that's your experiment. I know it's a lot of information. I'll take the recording and edit it so that you guys can review it again. Okay.